Good day, folks. Welcome to Bright Mind Academy, where we bring brilliance to every lesson. Now, in today's video, let's look now at a question 6, which is also chemical equilibrium, right? Mhm. So I want us to get used to this exam type of questions, okay? Yes. So now it says now sulfur trioxide gas is injected into an empty container, which is then sealed, right? So the following reaction takes place inside the container. Here's that reaction. So now the graph below shows the changes in reaction rates against time for the first 20 minutes. Now, before even looking at what and knowing which factor was that, let's try to think. Okay, the rate of the forward will decrease as time goes, the rate of the reverse will increase. Then at time 10 to 15 here, we know that equilibrium is reached. Equilibrium, yeah, equilibrium is reached. Okay, then here there is a disturbance that occurs thereof. Here, there is a disturbance that occurs. But now, this disturbance, it is an increase. But an increase in what? An increase in temperature or pressure. What do we know? How do we know that? Because both of the graphs increased. Okay? Can you see this one increased more, but this one also increased, but a little bit, okay? So if there is if both of them increase, it can either be increase in pressure or increase in temperature. It's either it is increase in pressure or increase in temperature. So the question is, how do we know which one is which? So which one was favored? The one that is favored is the one that increases more. Okay? Remember I said the one that increases more is favored, or the one that decreases less is favored. But in this case, we are talking with regards to increase. The one that increases more is favored. Which one is that? Can we see the solid one is the forward reaction? So let's see here. Here is 2 moles. Here is 3 moles. So if there is an increase in pressure here, which one will be favored? The reverse. Indeed, in this case, that's not the case. The forward is favored here, right? Forward is favored. Okay. So now it means now it favored. So it means now it is not pressure. Okay, it is temperature. But now, which one is favored? The forward direction is favored. And now we know an increase in temperature favors what? Increase in temperature favors endothermic, so that endothermic can do what? Can absorb that excess heat. So now it means if increase in temperature is favored, when if the temperature is increased, we know endothermic reaction is favored, right? And we can see from the graph that the forward reaction is favored. So it means the forward reaction it is endo. So it means the forward reaction it is endo here. I can say forward reaction it is endo. Write a note for myself here. I haven't looked at the questions, okay? Forward reaction it is endo, meaning the reverse reaction it is exo. Okay? Mm-hmm. From me looking at the graph, okay, and you being in a position of understanding your graphs. Remember, I said please look at the videos that I explained the graphs thereof, okay. Now 6.1.1 says write down the meaning of the double arrow in the equations. So remember that double arrow means what? Reversible reaction. Yo. Ah, reversible. Reversible. Like this. Reversible reaction. Please make sure that the spelling is correct, okay, when you write the exam thereof. The reaction should be reversible, okay? Then now what is represented by the horizontal lines between time t 10 minutes and time t 15 minutes? Between here, what is represented by this horizontal line? We know that it is what? Equilibrium is reached. Chemical equilibrium. Okay, it represents equilibrium or chemical equilibrium. Now they tell us at time t15, the temperature of the mixture in the container was changed. Can you see now we eliminated pressure and we said the temperature? Can you see we were being honest? We were telling the truth. So now the question is, was the container cooled or heated at time 15? Now, since there was an increase in temperature, it means that the container was heated, okay? If the container is heated, it means the temperature increased, okay? The question is the forward direction endothermic or exothermic? Now, we said the forward direction, it is endothermic. Why? Because now we know that if the container is heated, what will happen? The forward direction, if the container is heated, the temperature will increase, okay? And we know that an increase in temperature favors endothermic reaction, okay? So which one is favored between the two? Between the forward and the reverse? We say the one that increases the most is the one that is favored, which is what? Which is the forward. So if the forward direction is favored and the increase in temperature favors the endothermic. So can you see both of them are favored? So it means now the forward direction, it is endothermic. So we are in a position of saying the forward direction, it is endothermic, like that. Explain using Le Chatelier. Very important or very straightforward. Increase in temperature favors endothermic reaction. Okay. Then from the graph, the forward direction is favored. Is favored. Can you see favors favored? So it means now, favors favored. So the forward is endo because they are both favored in that particular case. They're off. Okay. Yes. So this is your reasoning. Interesting one. After 20 minutes, okay, here after 20 minutes here at equilibrium, there was something that was done. After 20 minutes, the pressure inside the reaction container increased. Okay, remember when we increase the pressure, we favor the side that produces less. Okay, so what happens? Remember the moles in here, it is 2, the moles in here, it is 3. So if there is an increase in pressure, remember the first thing that will happen. Okay, let's see what they ask from us. Redraw the graph below and indicate the effect that the increase in pressure will have on the reaction rate until the new equilibrium is reached. Okay, first thing first, when you draw, let me zoom out this. Both of them will increase, okay? Both of them will increase, but the one that is favored will increase the most, okay? But if there was a decrease, we were gonna say both of them will decrease, but the one that is favored will decrease less, okay? Now we come here and say there was an increase in the pressure of the system. If there is an increase in the pressure, both of them will increase, but we know Le Chatelier will do what? Will favor the reaction that produces less. So the reverse reaction will be favored. So if the reverse reaction is favored, it means here, when we come to our graph, the reverse reaction, which is the dotted line, will increase more, meaning this one will increase like this. Okay, let me try that. Like this. But this one, the dotted line will increase. Okay, the dotted lines will increase more. Okay, this is the reverse reaction. Will increase more. So now the question is, if Le Chatelier increases, if this increases more like that, there, allow me to say, okay, since this increases more, allow me to take this one and say it's gonna, okay, increase but less, okay? Okay. Now, if that happens now, do you agree with me that the concentration of this one will increase, but of this one will decrease? Okay. Yes. Now let's talk. If the concentration of SO2 increases, what will happen? Remember, if our reactants are more, the reaction rate will be higher. Okay, so if we have more reactants, if we have more reactants, it means the forward reaction will increase. Why? Because there will be more reactants to do what? To form the product. Okay, but on this side there will be fewer products. Okay, so if there are fewer products, the reaction rate will be lower, since well there will be fewer products to form the reactants. I hope you are following that. I'm saying the forward reaction will increase. Why? Because there are more reactants. Where is the forward reaction? Here is the solid one. It will do what? It will increase like that. Okay, but what will happen to the reverse reaction? What will happen to the reverse reaction? Since while we have less products, it means now the reaction rate will be low, the reverse reaction will be low, because now there will be less reactants to form back products, meaning the rate will decrease. So we'll do something like that until equilibrium is reached. Okay, remember here it should be more or less equal. Okay, this is what is going to happen. This is what is going to happen. Okay, remember, the first thing first, both of them will increase. Okay, both of them will increase, but the one that is favored will increase more, then this one will increase less. Okay, this is the forward reaction. This is the reverse reaction. Okay, after that, what will happen? Since well, Le Chatelier favored the reverse reaction. Le Chatelier favored the reverse reaction, meaning we are forming more reactants. So if you are forming more reactants, we know according to reaction rate, the topic that we did previously, it says now if you have more reactants, it means more collision per unit time will occur. Therefore, the reaction rate will increase. Therefore, you go to the forward reaction. Which one is that? Is the solid one. You say, okay, the reaction rate will increase. But what will happen to the reverse reaction? Similar. So we know if this one increases, this one should decrease. But I also explained why. This one is what we reach equilibrium again. I want to believe that you are following. Okay, yes, that is that. Now we are told that carbon and carbon dioxide are mixed in an empty 2 decimeter cubed container, which is then sealed. Okay. The following balanced equation represent the reaction that reaches equilibrium at 700 degrees Celsius. Oh, since well they use 700 degrees Celsius, not Kelvin. Okay, it's fine. We have that and that. Remember this, we won't include it on KC expression. Okay, on the table you can include it, it's fine. On the table you don't care. If it has information, then we can include it, but on the KC expression you do not include it. Very important. At equilibrium, it is found that the concentration of, this is very important. At equilibrium, it is found the concentration of CO2, it is 0.05 mole per decimeter cubed, and 0.4 moles of carbon are present. So it means we have at equilibrium number of moles of carbon, whereas at equilibrium we have concentration of CO2. The equilibrium constant for this reaction at this particular temperature, it is 0.05. Okay, yes. What percentage of carbon has reacted? Reacted, it is what? This is the same as change. Reacted is change. Remember, the one that reacts is the one that is going to change. So how can we find the percentage? So percentage of carbon that reacted is going to be the number of moles of carbon that reacted or change. Okay, let's say reacted divide by the number of moles of, what percentage of carbon has reacted? Okay, the number of moles of carbon initial. Then you multiply by 100. Okay? Okay, yes. The percentage of carbon that has reacted. Yes, it's going to be the one that reacted divided by initial, then you multiply by 100. But remember, I still repeat, the reacted, we will find it at change where we use mole ratio. Let me now quickly draw a table, a Rac table. Remember, we use a what? We use a Rac table, okay? Let me quickly draw that for you, okay? So that we will work nicely. Okay, now that I've completed our table of, let's me now in a position of adding what we have. Now, the reason I'll add carbon now on this table is because I have some information about carbon that might be important, okay? So I'll say carbon, which is a solid, okay? Then it's gonna react with what? Reacting now with carbon dioxide, which is a gas, forming for us two moles of carbon monoxide, okay? Okay, now let's fill up the information that we are given. We were given that at equilibrium, it is found the concentration of CO2, it is 0.05. Equilibrium, the concentration is 0.05, okay? Another thing that we were told is that the carbon and 0.4 moles of carbon are present. 0.4 moles of carbon are present at equilibrium. I don't need to calculate. Let me say, let me say, I don't need. Okay, you don't need to calculate this. Yes, since it is gas, so it is solid. Remember, it's, even if I can calculate the concentration of carbon, either way, I won't use it on the Kc expression. So what is the use of calculating it if I won't use it? Okay. So now, initially, we know that the product had 0. Okay. Initially the product had 0. And I know the Kc is given to me as 0.5. So I can get Kc and calculate this one here, because this one is very, very important thereof, okay? Yes. I'll say, okay, Kc is equal to concentration. What is my product? My product are CO. My product is CO. But now I'll have exponent 2. What are my reactants? My reactants are carbon and CO2, but I won't include carbon because it is a solid. Remember, on equilibrium constant, constant, I do what? I add only gases or aqueous. So I'm going to say I only have what? CO2 there, done. And I'm giving Kc as 0.05. What concentration do I want? I want the concentration of CO, okay? So I'm going to say, okay, I want the concentration of CO. I still square that. Divide, what is the concentration of CO2? I'm given as 0.05. Can you see that? 0.05. Therefore, if I wanted the concentration of CO2, it's going to be what? I multiply this to the other side. It's going to be 0.05 multiplied by 2, which is squared. Can you see? If I multiply this to the other side, it's going to be 0.05 squared. Then I can square both sides or square both sides, but I can see, okay, if I drop both those exponents, the concentration will be just 0.05 moles. Okay, if I just say this and this are the same, I just drop the bases. Okay. If I have a to the power of 2 is equal to b to the power of 2, it means b a is equal to b. Okay. Similarly, if I have a to the power of x is equal to a to the power of y. Since well the bases are the same, I can say x is equal to y, like that. Okay. Yes. You can also do mathematics. 0.05 multiplied by 2 or multiply by 0.05, you'll get 0.025. Then you'll square that. When you square root that, square root that, you still get 0.05. Okay, so yes, this is the concentration. So it's going to be mole per decimeter cubed. Very important. First mark will come here. Second mark will come here. How many marks are these? 8 marks. You are not done. I'm just telling you, okay? Then here you won't get it for now. You will get it as you use it. So we are saying, okay, here the information that we got is that the concentration here 0.0. The one that I just found, I completed in red, okay? So yes, remember I said for the reactant, it's going to be minus on the change minus, then for the product it's going to be plus. Why? I repeat, the reactants, we are using them, so they decrease, whereas the products, we are forming them, they increase. So what can I do? Remember, from here to there, I say, okay, if I want equilibrium concentration, I have to say number of moles at equilibrium divided by volume. But if I want to go back to number of moles at equilibrium, I have to multiply by that one. Meaning here I have to say number of moles is equal to concentration at equilibrium multiplied by my volume thereof. My volume is how much? 2 decimeter cubed. So I'm going to say here, okay, 0.05 multiplied by 2. I will get something like 0.1. So can you see where I get this? I said 0.01 multiplied by 2, then I get that. Okay, I also written the formula here. Okay, then here I will also get 0.1. Okay, this block, even if I ignore it, I don't care about this block. Oh, okay, I will care for it. Why? Because they wanted the carbon, the percentage of carbon. Okay, I will not ignore it. If they did not want anything about carbon, I would have ignored it. Then now they change, this will be 0.1 because 0 plus 0.1 will give me 0.1, right? Here, I use the what? The mole ratio. If I have 2 moles of carbon monoxide, I have 1 mole of carbon dioxide. So if I have 0.01 of that, sorry, 0.1 of that, I should have half because the ratio is 2 is to 1. Okay, what is half of 0.1? It is 0.05. Similarly, if I have 2 of carbon monoxide, I'll have 1 of carbon. Then what? I'll have 0.1 is to 1. So it's going to be 0.05 similarly. Okay. Then now what I need, remember I told you, Jorge, to calculate the percentage of carbon that has reacted, you're going to say number of moles of carbon that has reacted divided by number of moles of carbon initial. So I might jump straight to this block and say, okay, I need the initial moles of carbon, which is going to be X minus this is going to be that. Okay. X minus this is going to be that. So how much is going to be this? This is going to be, remember, if I'm from here to there, I'm subtracting. From here to there, I'm subtracting. It means from here to here, I should add. Okay. So 0.4 plus 0.045, it is 0. Sorry, 0.4 plus 0.05, it is 0.45. Okay. You can also do this and say it is 0.15. It is unnecessary, but it's fine. But now remember, I want, at the end of the day, I want the what? Number of moles of carbon that has, okay, percentage of carbon that has reacted. Gonna be, remember these are the number of moles that has reacted. They change. We said minus and plus because they react. Okay, so yes, they react there. The change is the one that has reacted. So now we're gonna say number of moles of carbon, let me say, that has reacted, divided by number of moles which are initial, okay, initial, then I multiply that by 100, then I get something like what has reacted for carbon. What has reacted for carbon, never mind the negative sign for now, it is 0.05. 0.05 has reacted. What are the initial? The initial, it is 0.45. Then I'll multiply that by 100. If I do my calculations very correctly, I will get something like 11.11, 11.11%. So this is the percent that has reacted. So far I have 5 marks. The other mark I'll get it where here, okay, here I'll get a mark, 1 mark, sorry, 1 mark here, 1 mark there, and remember this, we use ratio here, okay? So getting this one as well as getting the ratio, I think the marks are fine now. 1, 2, 3, 4, 5, 6, 7, 8, okay? Yes. So we have found the percentage of carbon that has reacted, which is 11.11. Okay. So yes, thank you very much. That's all for this question. Please continue watching my videos. I hope you are enjoying them. Okay. Yes. Thank you.